Hello everybody, and thank you for attending my talk entitled Integrated Long-Range Thermal Bimorph Actuators for Parallelizable Bio-AFM Applications. So here's an outline of my talk. First I'll give you a bit of a background of my project, state-of-the-art, how the actuator working principle is functioning, device fabrication, results, and then finally summary and outlook. Okay, so the basis of this project is actually that cancer affects the Young's modulus and adhesion force that a cell is exerting, and that we can quantify this very precisely using AFM cantilevers, which was shown in this study here. And here you see an AFM cantilever approaching a tumor cell. Here's a normal cell. Now they put these in these two histograms, Young's modulus here on the x-axis. So these are the healthy cells, these are the cancerous cells. So you see that the distribution is very different. And so this has inspired a lot of hope of potentially learning new things about cancer, in particular about the invasiveness of cancerous cells and of assessment of treatment and so on. The only problem is that these measurements take a lot of time. So in this project, what we are trying to do is to increase the throughput by parallelizing the measurements using arrays of cantilevers. So you can imagine you have a type of pre-patterned substrate where the cells are only attaching at kind of certain sites with a certain pitch matching your cantilever array. And we read out our structures using this type of interferometric setup. You're basically illuminating a full field of view with coherent light. You use a reference to generate interference patterns, and in this way you can very precisely determine the Z position of your structures. Now the advantage of this is mainly that you don't have to align a laser for every cantilever, so it's very scalable. We are at 2 by 2 millimeter square, and the limitation here is really the resolution of the camera. So you could potentially improve that. The only constraint is basically that you need to look at a planar surface, because and again, this is related to the resolution. If you have too much of a tilt on your structures, then the interference fringes become more narrowly spaced, and eventually your resolution does not allow you to distinguish them anymore from each other. Here we have one of these cantilever arrays that was used previously by Melanie Fab. So it's a passive 2D array. So you basically approach globally just by approaching the entire chip to your cell substrate. And these are 16 different approach curves. So the 16 cantilevers in the array. So what you can note is that there are quite a lot of large variations in contact points between different cantilevers. You see that some are maybe touching at -3 or so, maybe even earlier, whereas some have hardly started touching, which means that basically you're going to apply very different forces to different cells, which is going to weaken your data finally. So the only way to really get around this is to have an individual actuation of each cantilever, which is actually what I'm doing. And if you take into account all the different factors that could induce variations, such as difference in cell size and fabrication-related variations, you can come to the conclusion that about 10 micrometers of static actuation range would be sufficient to compensate. I spoke about the tilt, so we set a maximum of about 3 degrees. So you're starting to get a picture here. Something needs to displace 10 micrometers, which is quite a lot already, but it needs to stay planar, cannot tilt more than 3 degrees. And then the unwanted coupling between actuator and force sensor should of course be very small, and or vice versa, also small. The actuator should be inert to biological systems. So now we're talking about thermal actuation, as you will see. So the elevation at the cell should be, let's say, less than 10 degrees. And the crosstalk should be between different actuators should be very small, of course. So the state of the art, now here's one study where this thermally actuated cantilever was used to image yeast cells. So you got your actuator coil here. So it's a heater as well as a stress-inducing element, and you got a piezo resistor here for readout. So what you could see from this characterization, this actuation method, is that you could get quite large deformations. It was compatible with work in liquid, and you could also see that the heat dissipation was very efficient. But here the tilt is, of course, much larger than what we can accept. So we looked at a different study where you have this kind of patchwise structuring on top and bottom. So you have a structural layer here of, let's say, silicon nitride, and then you got metal layers. So because of the difference in thermal dilatation coefficient, if you change the temperature, then you induce some stress, which is going to bend your structure. But as these two are balanced, you're actually going to be flat at the end point. And you can use this to make this type of winded structure, which enhances your total displacement. And this has also been, this type of structure has also been realized as an actuated system, just by basically integrating a heater in the center. So, and this is an optical scanner. So just to kind of summarize the working principle with a small animation, let's say that you got, this is the bottom layer here and top layer. Now you change the temperature, and then, so as you can see, this is what will happen. It'll displace in Z, but remain planar just at the end point. Okay. And as I was showing, you could potentially so put the two things together. So here's your force sensing cantilever, and here's your actuators, springs. Basically, you got 4 of them. Okay. And so here you can. This is the design that we are using. So you can imagine that. Here the metal layers are working both as heaters as well as stress-inducing elements, and just through this kind of alternating patterning, we are able to make this type of Z displacement, while this central structure doesn't change its tilt. Okay, so moving on to fabrication. Okay, so you see a cross-sectional view on the left, and here's a alternating between bottom and top view. We start out with a silicon 100 wafer with a silicon dioxide coating on the backside, about 1.5 micrometers. We pattern, we make a hard mask for the final release of the structure, and we're also featuring this type of gray mask, which is actually to thin down the silicon in a very kind of tunable way, which we do because we want to have a certain optical access. I will explain more in detail in the next slide. Now, moving on to back on the top, we pattern our first heating layer. Okay, well, platinum. And we deposit some PE-CVD silicon nitride, which we structure using dry etching, and then we deposit by liftoff. We pattern the top heater layer, and then using Bosch process, and then removing the hard mask layer, and then releasing in KOH, we release the structure. Okay. So the finalized structures look like this. So you got your heating, actuating springs here, a central platform, and then this force sensing cantilever here. And we added this structure, which is really just kind of following the central platform, but in an attenuated way. And this is to allow us to more precisely determine the position. It's related to the readout method. Okay, so if we zoom in on this part here, okay, so we can see more kind of precisely how this is the top layer here, and you see some kind of imprint of the bottom layer. And we also made some first 1D arrays, very simple arrays, a 1x2 array, which was possible, but we also learned that we really had to change a few things in the fabrication to improve the yield, because obviously the yield is very important for manufacturing arrays. Okay, so a few more details about this backside gray mask that I talked about. So what we use here is actually that we have very narrowly spaced, very thin slices, and so we use the so-called reactive ion etching lag effect, which means that if you have smaller apertures, then your etch rate is going to be lower. Okay, so your etch rate here is going to be higher than it's going to be in one of these openings here. Okay, and what that means is that you can, in a very arbitrary way, determine the final thickness of the silicon. Yeah, so this is if you make a kind of an anisotropic dry etching, and then you remove your hard mask, then you end up with some type of amphitheater structure like this, and then you can release it in KOH, and then you see a structure here, and you can see that it's quite nicely opened. So we still have some silicon here, which is giving us mechanical fixation. Yeah. So over to some final results. So we characterized the structure first of all in air using an optical profilometer. So here you see for different voltages, so that we reached about 17 micrometers of maximum displacement. Yeah, we could also confirm that this optical reference structure was following very linearly. Okay, so here's just to give an idea of how it's moving. So this is basically the structure moving in and out of focus. So you can see that, okay, these are interconnects here, and you can see that, yeah, this spring is following as well. Right. Okay, so on this, well, then we wanted, of course, to bring this into water. And in order to be able to do that, we had to passivate our electrodes. So we deposited a uniform parylene layer. Then we brought it into water, and we could confirm that it was working. However, of course, the thermal dissipation is much more efficient in water. So, of course, the deformation is not as strong. So we were very happy that this was working, but of course, perhaps we needed to work a bit more on the optimizing the thermo-mechanical sensitivity here. Okay, so maybe you're asking yourself the question now, so how hot does it actually get? Are we maybe frying ourselves like these eggs here? Of course, we made many simulations to try to help in the design of the structure. So one of the simulations we did is this type of 1 millimeter cube volume. Half is about half is water, half is glass, and in the center you have this heating element. Okay. And okay, so if you let this, you apply as much current as you could possibly put on this, and you let it reach its steady state solution, then we found that, okay, so we get about 54.5 temperature elevation at the center. But what we also can see is that if we move away from this structure, then the temperature elevation is much smaller, so about 9.1 degrees Kelvin, 100 micrometers away, which means that, okay, potentially we could actually find what I like to call a biocompatible thermal window where we have enough deformation, but we're not heating ourselves too much. Okay, so as a summary and outlook, so we could successfully fabricate actuated long-range devices. The parylene passivation made this water compatible. Simulation suggests a biocompatible thermal window, and so challenges that remain is that the thermomechanical sensitivity needs to be enhanced. We need to fabricate a new generation with tips, and okay, so this is in progress, and now we're using a new electrode material, which should give us about 2.5 factor increase of deformation, also using a different actuator shape, which should get us up to that 10 micrometers. So as last slide, okay, so I'd like to acknowledge the Nanoterra initiative for financing this project, the Center of Micro Nanotechnology at EPFL, my colleagues at LMICE1, of course, and thank you for your attention.
Okay, thank you very much.
Questions?